Welcome to this first video about semiconductor physics. During this course, you will learn about the properties of a semiconductor as a photoactive material for solar cells. I will introduce you to the topics that we will cover in the coming 4 modules. Semiconductors are materials used in many applications. We can find them in electronic devices such as diodes, transistors, or integrated circuits. But for us, they play a crucial role as active materials in solar cells. But what is a semiconductor? Let's define this term. We will do this by looking at important material properties that define a semiconductor. When we look at the ability of materials to conduct electricity, they are generally divided into 3 classes: conductors, semiconductors, and insulators. A semiconductor is a material whose electrical conductivity is lower than that of a conductor, but higher than that of an insulator. One example of a semiconductor material is silicon. Solar cells made of silicon dominate the photovoltaic market. Therefore, we will focus our attention on silicon as an example of semiconductor material. We will explain its properties and use such material to describe the working principle of a solar cell. A way to control the performance of a silicon-based device is by doping the material. Doping is a process to manipulate the concentration of mobile charges in a semiconductor. This is done by replacing silicon atoms in the lattice by atoms of a suitable element. Doping will increase the electrical conductivity of a semiconductor. Common dopant elements for silicon are boron and phosphorus. The presence of boron or other group 13 atoms is known as p-type doping because it increases concentration of positive charges. The use of phosphorus or other group 15 atoms is called n-type doping because it increases concentration of negative charges. We will go further into the consequences of doping in the coming week. In the following, P means extra positive charge carriers. N means extra negative charge carriers. To describe the properties of a semiconductor, we use energy band diagrams. They are useful representations of the allowed energy states for electrons in a material. We will use them to describe the main properties of silicon and all properties involving the transport, generation, and recombination of charge carriers. Since the accurate form of these diagrams is rather complex, for simplicity they are usually represented as shown here. We will discuss the meaning of this diagram in the coming videos. Since electric currents only arise from a net movement of charges, we will first discuss the mechanisms of charge transport. In a semiconductor, we distinguish between carrier transport by drift and diffusion. Drift occurs in response to an electric field. Diffusion, on the other hand, is based on a thermal motion and is driven by a difference in carrier concentration at different places in the device. Both processes are important for understanding how charges move around in a solar cell. This topic will conclude the first set of lectures. The second part will be dedicated to 2 very fundamental processes for photovoltaic conversion: generation and recombination of charge carriers. Let's briefly introduce these concepts. In most semiconductors, the atoms are kept together by covalent bonds. A covalent bond is formed when 2 atoms share 2 electrons, each atom contributing 1 electron. We call these electrons valence electrons, and they are immobile while forming a bond. The energy states of valence electrons are in a valence band of allowed energies. Through different forms of excitation, such as illumination, these electrons can be liberated from bonds via a process known as generation. In band diagrams, this process can be visualized as an electron moving from a state in the valence band to a state in the conduction band. An excited electron leaves a vacant place in the valence band, and this vacant place is called a hole. You will learn a lot about this process and how it works in solar cells. Generation is in high competition with its opposite process, recombination. This essentially means that excited electrons return to form covalent bonds. The Venn diagram is a good means to visualize this process. There are three main mechanisms of recombination, and you will learn all about each of them in future videos. This will conclude the second module dedicated to semiconductor physics. In the third part, you will learn what happens when we put a p-type semiconductor and an n-type semiconductor together. This forms a p-n junction, an extremely important component in semiconductor devices. This is the most important building block of most solar cells. P and n-type doped layers are commonly applied together in a device, and there are several reasons behind this choice. First of all, as we said, doping enables us to manipulate the concentration of charge carriers. We can use boron atoms to make silicon p-type. This increases the concentration of holes. In a similar way, we can use phosphorus atoms to make silicon n-type. And this increases the concentration of mobile electrons that occupy energy states in the conduction band. You will learn what happens when these two materials come together. The p-n junction, as shown here, is important for separating photo-generated electrons and holes. The properties of the p-n junction change when voltage and illumination is applied. You will learn how these effects take place in a silicon-based p-n junction and how the junction can be used as a solar cell. p-n junctions are not the only junctions that are present in a solar cell. Photoactive layers are also placed in contact with metals. This will be one of the main topics of the final module dedicated to semiconductor physics. You will also explore other advanced semiconductor topics like the recombination current J0 and the junctions formed between two different semiconductor materials, the so-called heterojunctions. At this point, let us begin to look at the configuration of common solar cells. Generally, a moderately doped semiconductor layer is sandwiched between other highly doped layers. As we mentioned before, this is done to promote the separation and collection of photo-generated charge carriers within the device. A solar cell has to be connected to an electrical circuit, and this external circuit where the electrical current generated by the solar cell can perform useful work. This is done by applying two metallic layers, one at the front and one at the back of the device. These are called front and back contacts. Their presence is necessary to extract photo-generated electrons from a solar cell. In the last module on semiconductor physics, we will understand what happens at the interface between a metal and a semiconductor. We will start with an explanation of the energy band structure of metals. By doing so, we will introduce the concept of the vacuum level, the work function, and the electron affinity. Then we will explain to you how to make a metal semiconductor junction and what its implications are on the device performance. Lastly, we will focus on the difference between ohmic and Schottky contacts. In this video, I introduced the main topics of the semiconductor physics section of this course. This will cover 4 modules. At the end of these modules, you will be an expert in semiconductor material properties. You will understand transport, generation, and recombination processes taking place in semiconductors, as well as the p-n junction and the metal semiconductor junction. With this knowledge, you will be on your way to becoming an effective solar energy engineer.